All right, I want to look at this one, which speaks to the issue of hybridization. Which of the following molecules contains a central atom with sp2 hybridization? Remember, sp2, on this side, sp2 implies the hybridization of one s and two p's, which leaves an extra p out of the party. But the geometry, the electronic geometry of this one is trigonal planar. So in order to find trigonal planar, it looks like the Lewis dot structure for these is complete. It has all the lone pairs as well, and that's good. So for trigonal planar, we just need to look for a central atom that has three groups around it. And it looks like that one doesn't work. That one works. 1, 2, 3. But it's octet deficient. This one has 4. See that extra lone pair down here. And this one has 1, 2, 3, 4 around each nitrogen. So B is the only possibility for sp2 hybridization here. Cursor out of the way. All right, let's see if I can page. Do I need to do 2? I don't have that one marked. I'll have to do it while we're here. Which of the statements about N2 is false? Okay, let's see what type of statements they're making. It's a gas at room temperature. Well, yeah, that's true. If it wasn't, we wouldn't be breathing it. Oxidation states. Okay, we need to calculate those. 1 sigma, 2 pi's. Okay, so we're going to need the probably the Lewis dot structure and calculate the oxidation state. Oh, that's easy. Oxidation state for an element in its most stable form at 1 atmosphere pressure and room temperature. That's it. That's the gas. When it's like that, the oxidation state's 0. So we know that one's false. B is false. That was true. 1 sigma and 2 pi's. Well, we've drawn it enough. Like that. So 1 sigma is this one, and these are the 2 pi's. It can combine with H2 to form NH3. Well, yeah. That's one of my favorite reactions, the Haber process. Has 2 pairs of non-bonding electrons. Yep. 1 pair, 2 pair. Okay. I do want to look at number 3. I think. Sure. Yeah. Got that one marked. Okay, we're going to use this as our skeleton. And if there are any lone pairs, they're not drawn in. So we might need to do that. Let's see what it's asking. What's the hybridization of the carbon atom that is double bonded to oxygen? Okay, so it's identifying this one. And that one, carbon tends toward octet completion. It's pretty consistent there. So we have 2, 4, 6, 8. It's got its octet. Okay, so the hybridization on carbon, well, it has 3 groups. So it has to be trigonal planar, correct? Which means it's sp2 hybridized. So the answer should be B. What about the others? That's just while we're here. That one's sp2. 1, 2, 3, 4. That would have to be sp3. 1, 2, 3, 4. sp3. This one has 1, 2. That's sp. All right. 4. Using the same, like the same model. I'm gonna have to scroll that one. My page will cut it off. Let's see. It's got a second one down there. What if I do like this? Yeah. Yeah. Okay, now I can page to 5 in case I need it. Okay, 4. This same molecule, what's the hybridization of the nitrogen atom? Oh, we didn't do that one. Hybridization on nitrogen. Okay, so we need to know, does it have any lone pairs out here? 2, 4, 6, more than likely. It does have a lone pair. Okay. So that means it's sp hybridized. A. Let's see. Now I don't have 5 marked. Oh, we already did it. Hybridization on each of the carbon atoms. 1, 2, 3, 4, 5. Oh, it's a different molecule. Yeah, it's a different molecule. We still have sp hybridization here. So that means it's either this one or this one. And this one is 1 for organic molecules. I think I said before, but if the hydrogen in this, the way we write organic compounds, if we put the hydrogens after a carbon, they're bound to the carbon. They're not bound to the next. They're bound to this carbon, not to that carbon. They're not interspersed. They're like this. And then you would have this one over here. That's just convention, the way we write organic compounds. Okay, so this one would be sp3 hybridized. So this one, it would have to be A. Let's check the rest of them to see. What's this one? Let's see. 1, 2, 3. This one would be sp2. Yep. 1, 2, 3. This one would be 1, 2, 3. That would be sp2 also. And this one would be 1, 2, 3, sp2. Okay, so A is the correct answer. Let's see. 6. There we go, 6. Hybridization of selenium in F6. So we got to draw the Lewis dot structure. Selenium in the middle. We got 6 fluorines. Okay. Selenium, let's see, fluorine is 7 valence electrons. So 6 times 7 is 42. Selenium is in the sulfur group, so it should have what? 6? Well, oxygen actually. Yeah, it should have 6. So we have 48 total. 2, 4, 6, 8, 10, 12. So that's 6, 36. Okay, we've already counted for these. If we put 6 more around each one of these, 6 times 6 is 36. So there are no lone pairs. And that means that selenium has 1, 2, 3, 4, 5, 6 orbitals that have to be symmetrically arranged. That means it's octahedral. And that means that sp3 is not enough. That's only 4. So we need 2 more. D2sp3. We'll get the selenium taken care of using this tweak to the valence bond theory. Okay, that's 6. How about 8? 8, I'm going to have to. Yeah, I wanted to look at 8 because it can be kind of squirrely. Yeah. this is our skeleton, right? And what that means is there are no other atoms in this molecule. That's it. We don't have any hydrogen stuck in there. We're dealing with just these 6 carbons and 4 nitrogens. Tetracyanoethylene. Now, if you know organic compounds and how to name them, you can write that compound. But in this course, we haven't learned how to do that. So we have to approach it a different way to write the Lewis dot structure. How many atoms are sp hybridized? So sp hybridized means that there's probably a triple bond in there somewhere. Okay, so let's say we've got 6 carbons is 4 times 24, right? The marker that works. 24 for the carbons, and then the nitrogens are 5, is it 4 times 5 is 20? 44 electrons. Check myself. Yeah. Okay, so 44 electrons means that we look at what's the skeleton so far: 2, 4, 6, 8, 10, 12, 14, 16, 18. So that's 6 and 2, 26 electrons yet to be placed. Normally we start from the outside and move in, and that's okay. If we put 6 more around each nitrogen, then that's 4 times 6 is 24. Right, so we have 1 pair of electrons that we don't know what to do with. If we follow the convention and move to this carbon, one of these carbons, and put that lone pair, then notice that these carbons, 2, 4, 6, they're not going to have access to that lone pair. They're not going to be able to make an octet. So what we need to do is put that lone pair down here. That way it could go either direction. It could go this way, it could go that way, it could go this way to make a double bond. So, but let's work from the outside first. Now that we've got all our electrons placed, here, 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 here. Now what we can do is, in order to make an octet, we could move a pair here and a pair here and make a triple bond, like that. That would satisfy the octet here and there. And that would leave this lone pair free to satisfy the octet for these 2 central carbons. So if we do that for each one, there we go. Now we can move this one over here and make that double bond. And that gives us octet, 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 all the way around. That was the part of this question that I thought would trip you up, because if you follow a procedure, you're going to put the lone pair on one of these, and then you never be able to complete the octet for those 2 central carbons. So now let's go back to the question. sp hybridization, we need a triple bond, or we need 2 groups around the atom. And in this case, we have 1, 2. This one's got 1, 2, 2. Okay, so this carbon and that nitrogen are both sp hybridized. 1, 2. So that's 2, 4, 6, 8. So it looks like we got 8 atoms with sp hybridization. Yeah, 8 for 8. And of course, these 2 would be sp2 hybridized. And that covers everybody. Okay, let me see if that. Just checking to be sure that diagram is not, well, yeah, it is going to be needed again. Let's skip to 23. Let's see if I can do that. Yeah. I wonder if I can scroll it. Not quite. It just doesn't line up, does it? Oh, all right. It's using the same skeleton. So I'll just quickly draw it in. Double bond there, triples here, 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 here. Okay. So now we're back to where we started. But this question uses that Lewis dot structure to answer different questions. How many sigma and how many pi bonds are in the molecule? We know that only sigma bonds can be, you only have one sigma bond between two atoms, but you could have one or two pi's. So the sigma bond here is are just whatever we started with for the skeleton. It's 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 sigmas. It's either this one or this one. Now how many pi's? Well, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 sigmas and 9 pi's. So D's your answer for that. Now I can go back. I think. Let me be sure there's not another one scattered in here. Okay, we're good. So let's go back to number 9. Can I do that by paging? Yeah, there we go. All right, simple question. With this, with what we know about orbitals, and well, actually, this works for the answer here would have to be based on our hybridized orbital model. If we go to the molecular orbital model, then it doesn't make much sense. So if we use the atomic orbital model from the valence bond theory, then the pi bond results from overlap of unused p orbitals. So let's see, overlap of 2 p orbitals not along the axis. That'd be parallel orbitals, sideways overlap. There you go. Of the p orbitals. Because only sigmas can overlap on axis. Okay. Let's get down to 12. And 12 introduces our shorthand notation for molecular orbitals. Right. Did we talk about this? Probably didn't. Did we talk about it a little bit? Okay.
Maybe I remember it from the first.
Okay.
Maybe I saw it on here.
That's fine. I didn't make a point of it during the lecture, but this is a shorthand notation. It's similar to the electronic configuration that we learned for individual atoms. You can take the energy diagram that we constructed for molecular orbitals and just turn it on its side with the low energy on the left, increasing energy to the right. And these are the number of electrons that can be placed in each one. Sigmas can only have 2, and pi's can have 4. So that says that this pi is full. This pi only has 2. And when you see 2 in a pi orbital, whether it's pi bonding or a pi anti-bonding, we use Hund's rule, and those 2 have to be in separate orbitals. So they're unpaired. This is important for interpreting whether or not they're paramagnetic or diamagnetic. Okay, so let's see what the question is. This diatomic species has this molecular orbital configuration. What's the bond order for the species? Okay, so this one's easy. Remember how to calculate bond order. You just take the bonding electrons, 2, 4, 8, and subtract the anti-bond. 2 is 4, divided by 2. So that should be 2. So the bond order here is 2. Let's see. Oh, we got to do 13. So I guess I better scroll. Yeah, that's a good place for it. I'm gonna have to get another marker. For some reason. Crapping out on me. 13. As the bond order of a bond increases, get higher bond order, the bond energy does what? According to the answers, it can either increase or decrease. The bond order increases, the bond energy increases. It takes more energy to break the bond. So it's either A or C. I don't think more information is needed, but it's there if we need it. And the bond length, what does what? If you increase the bond order, increase the bond strength, the bond distance is going to decrease. So it'd be energy increase, decrease, C. All right. Let's go down to 15. There we go. With another shorthand molecular orbital structure. And you can also tell from here whether this one is listed as SP mixing or not SP mixing. If you look at the 2p origins for these, if there's no mixing, then the sigmas are going to be on the low and the high end of the energy. And then the pi's are going to be in the middle, pi lower than pi star. That's a signature for no mixing. And that makes sense because this is fluorine. You know, we don't get mixing for oxygen or fluorine because the SP energies are too far apart. Well, actually, the proper approach would be the sigma pi energies are too far apart. But for some reason, SP mixing has kind of crept into the language and can't get rid of it. Okay, how many unpaired electrons in the F2 2+ ion are based on molecular orbital theory? If the order of molecular orbitals is this, okay, so we're given the order here, but we're not given the number of electrons and the position of electrons that go in there. So what we have to do is say, how many electrons do we have to place in here, and just use the Aufbau principle and follow Hund's rule and go left to right. So fluorine normally has 7. 2 times 7 is 14. But we've made a 2+ ion out of it. So we've lost 2 electrons. So we got to put 12 electrons in there. All right, this one can hold 2. And they're paired, obviously. This one can hold 2. This one can hold 2 more. So that's 6. We got 6 more to go. This one can hold 4 maximum. And they're all paired. And so this one we have 4, 6, 8, 10. We've got 2 left over. So we put 2 here. And to understand how many unpaired electrons, you have to remember that the pi's always have 2. So these 2 will go in like that. They're unpaired. So How many unpaired electrons? There are two. Two unpaired electrons. Yep. Okay. Let's see. No, I skipped a bunch of them. Must be a lot of repetition. I'm going to have 22 next. There we go. Hybridization of, okay, so we're going to backtrack a little bit. Hybridization of chlorine in ClF2 plus. Okay, so we have Cl as our central atom, and then we have an F on either side. Okay. Normally we would have 3 times 7 is 21. 21 electrons. But we've got a plus charge. That means we lost one. So we only have 20 electrons. Okay, so we work from the outside. Let's see, we've got, well, we'll do it this way. 2, 4, 6, 8, 2, 4, 6, 8. 16. 4 electrons left over. So we put a pair there, a pair there. Okay, so the hybridization on chlorine is sp3. It's got 2 bonding groups and 2 non-bonding. So it's sp3 hybridization. Let's see here. We did 23. So we'll skip to 26 is my next targeted one. Yeah, it's going to misbehave, of course. '26. So here we have a skeletal structure, and similar to the last one we did with just a skeletal structure, this is all there is. There are no other atoms in this molecule. Draw the little structure and answer the following question. How many pi bonds does the molecule contain? Okay, so we have 2 carbons with 4 each is 8. All right, let's try this one. That's not much better, is it? Let's try this one. Okay. And then 2 nitrogens at 5 each was 10. So we have 18 electrons. Okay, so we've used up 2, 4, 6. 12 electrons left. So 2, 4, 6, 2, 4, 6, all gone. Now we got to try to make an octet. We got nothing to work with in here, but we can put a pair here and a pair here, like that. 2, 4, 6, 8, 2, 4, 6, 8. Let's move these 2 over here like this. There we go. And that gives us, how many pi bonds does the molecule have? So that's 1, 2, 3, 4. Oh, it's gonna leave a ghost. That's why I don't like to use brown. Let me grab out a fresh black. Good thing I can buy these in bulk. Okay, that was 26, 27. Okay, it's going to run high. Which of the following molecules contains the shortest carbon-carbon bond? Okay, let's see if we've got similarities here. They're all, the top 3 are carbon hydrogens, hydrocarbons. Then we have C2CL4. Okay. Well, let's look at each one of them. Get this one started. C2H2. We draw this one in Lewis dot structure. And we're going to have hydrogen here and hydrogen here. So that's 2, 4, 6. 6 electrons used out of 8, 10. So we have 4 electrons left over. There we go. Okay, we can't go this direction, but we've only got 2, 4 here. We could move this one over here and this one over here. Now we have an octet. That, by the way, is acetylene. And it's going to have a pretty short carbon-carbon bond because it's triple. This one takes that and does this with it. And you can check my electron totals. Yikes. Sprung a leak. So I can get in on my clothes. It's okay. It's easier to get off your hands than your clothes. Yeah. It's up in my cap. So let's do this. Set that aside. Okay, back to our topic. So the next one has the bond had energy has decreased and the distance has also increased. And then for the next one, C2H6, we just have like this. Okay. So now the bond is further apart and weaker. This one's the kicker, C2Cl4. C2Cl4. I think we need to draw this one. So that's 2 times 4 is 8, and 4 times 7 is 28. So that total is 36. Let's see. 1, 2, 3, 4. There. Okay, correct. 2, 4, 6, 8, 10. 26 left over. How about that? I think that's better. Okay. We can put 6 around each one of these. 4 times 6 is 24. So we have 2 that have to go here. Okay. And to make an octet, we just move them over. So it's analogous to these. Okay. See what the author is getting at here. Oh, okay. We don't have a problem because we have this one. That's going to trump both that one and that one. If we didn't have this one, then we'd have to say which one of these would make the stronger bond. And if that were the case, I'll just use this as a teaching moment. What you find is hydrogen electronegativity is a lot less than chlorine. So the chlorine would tend to draw electron density away from those carbons and weaken the bond. So in that case, if we only had this one, which is ethylene, and this one is tetrachloroethylene. If we had those two to compare, this one would be the shorter, stronger bond. So it would retain electron density in the bond rather than being drawn out by these chlorines. But the way it's written, acetylene is your answer. Okay, let's see, 26, 27. So you can, wait a minute, did 27. 29. Okay, 29 stands alone. I was checking to see if it referenced this stuff up here, but it doesn't. It's on its own. Which of the following species is paramagnetic? Okay. In the interest of saving your time, I've included the exam will also have this. Is that chart listing the homonuclear diatomics in the back? So you can look at that one, and that will cover carbon, oxygen, difluorine, but it doesn't cover lithium. Okay, so what we're going to see is for carbon, we have, let's see, we have all paired electrons. You can see from the diagram. So all paired means this one is diamagnetic. How about O2? O2 has 2 unpaired electrons. So this one is paramagnetic. F2, they're all paired. So this one is dia. For lithium, what we have to do for lithium to answer that question with the limited information we have is look, lithium is here, dilithium. Okay. So lithium would have a commonality with hydrogen. I think. Oh, no, there it is. I'm sorry, I see lithium. So lithium has sp mixing. And we would have to draw it out. So lithium, let's do that. Lithium has, let's see, sigma, here it is, sigma 2s, sigma 2s star, sigma 2p, pi 2p, and then, oops, nope, it's got mixing. So it's going to have pi 2p first, and then sigma 2p, and then pi star 2p, and then sigma star 2p. So that's the order. We flip these two right here. Okay, so how many electrons? I've included only the 2, the second level. So the first 2 electrons we're going to leave out of lithium. Lithium has, well, actually, lithium only needs this one, right? Because it's only got 2 electrons. So lithium is paramagnetic. Excuse me, diamagnetic. Okay, that was easier than I thought it would be. So which is paramagnetic? It's just oxygen. So let me go back to 29. Yeah, there we go. Anyway, that's what happens when you overthink. Okay, next one I have marked off is 30. And I'm going to have to scroll that one. How many can I get? I get 3 of them on there in case I need them. For many of the following for how many of the following does the bond order decrease if you add one electron to the neutral molecule? Okay. So I would suggest simply go into that diagram again, which will give you the diboron. Okay, so got that one, that one, that one, and that one. And the diboron would have, let's see, sigma, sigma star, pi. Sigma, sigma star, pi. This is 2s, 2s, 2p. And the boron would have 3, 6. 2, 4, 6. Okay, let's do these first. Carbon then would be similar. Except it has 4 each, so it's 8. 2, 4, 6, 8. Phosphorus. Okay, where's phosphorus going to be? Phosphorus is under nitrogen. So if we look at nitrogen, and we have to assume that it's going to behave like nitrogen, which would be mixing. So here's the nitrogen. It has sigma 2p extended here. Actually, sigma 3p for phosphorus because it's in the third period. Sigma star, 3s, and sigma 3s. So for this one, we look at the valence electrons only. And phosphorus is going to be the same as nitrogen. It's going to have 5, and 5 is 10. So we have 2, 4, 6, 8, 9, 10. And then difluorine is here. It goes all the way up to, with no mixing, is, let me move it down here. Sigma 2, yes. Sigma star, 2s. Yep. And hold on a second. Sigma 2p, pi 2p, and pi star 2p, and sigma star 2p. And fluorine has 7 each, so that's 14. 2, 4, 6, 8, 10. Did I say 14? About 14. 2, 4, 6, and 8 is 14. Okay, so we don't need this last one. Yep. Okay. Now that we have their configurations, we can say, what's the bond order? Well, in the interest of time, how many of these would decrease? Bond order would decrease when you add an electron to a neutral molecule and you want to equals bonding and anti-bonding divided by 2. If you want to excuse me. If you want to decrease the bond order, then you need to have more anti-bonding electrons than you did before. So if we add an electron to any anti-bonding orbital, it's going to decrease the bond order. So let's see, if we add, we've got room here for this one, right? But that's a bonding. So this one's going to increase. This is increase. This one, we can't add any more to this one. But what's next? What's next is sigma. If we add one to that one, it's going to increase the bond order. This one, that one's full, right? So we have pi, 3 pi sigma, pi star is our next one. Is that right? Because it's got mixing? Yep. If we add one to this one, it's going to decrease the bond order. And this one is full. But what's above here? Let's see. That. It's also. We add one to this one, it's going to decrease. So 2 of them will decrease bond order if we add an electron. If we make a negative ion out of it. Let's see, does that jive with the key? 30. Yes. Okay. So we didn't actually have to calculate the bond order. You can do that if you want, but a reasonable and quick approach is to say what happens out beyond. Are you adding to anti-bonding or bonding? Okay, that was 30. 31. Which of the following has the largest bond order? Okay. We've calculated this one before. We know it's 3. But to do the others, we need to know we need to write. Here we go. Let's write shorthand. Let's just do it like this. Let's write it for all the N2s. For this one, it would be sigma star. Then we would have I2P, sigma 2P, and pi star 2P, and then sigma star. I think that's going to cover all. Yeah. Okay, so nitrogen is 5 each. Normally we would have 2, 4, 5. Right? Oh, that's not right. What did I do wrong? 10. 2, 4, 6, 8. So there we go. All right, so that's N2 up to this point. If we add an electron, where is it going? It's going to have to go here. So this one decreases actually to 2.5. How about if we add 2 electrons? Both of them are going to go here. So it decreases the order to 2. How do I know that? Because if you add 1, you're subtracting half. 1 divided by 2. If you add 2, 2 divided by 2. Subtract 1. If we subtract an electron, right, we're going to take it away from a bonding orbital. So that also goes down by half. If we're going to subtract 2, then we take 2 from the bonding. It's also going to go down 2. So which of the following has the largest bond order? The neutral dinitrogen atom, molecule. Okay. 31. I'm going to skip way down. You want to look at these others? Let me see. Did I actually skip them or I just ran out of
So those are bond order questions.
Yeah, it looks like most of them are. Let me see if one of them might be interesting. No, number 44. Which of the following contains the strongest bond? We already did the information, got the information that would answer that question. It's the one with the largest bond order. So it has to be A again. And 45. Which of the following has the highest bond dissociation energy? That's also A. It's just another way of saying the same thing. Let's see. Oh, I saw an interesting one. Let's fill in the blank starting with 49. They're just memorization. Hybridization for this molecule would be sp2. Let's see. I don't see anything. Maybe we would look at 455. The concept of what is required for certain molecules because of the localized electron model assumes electrons are located between a given pair of atoms in a molecule. That's talking about resonance. You can draw, since they're localized, you can draw two or more, for many molecules, you can draw two or more equivalent Lewis dot structures. And in that case, they have to resonate in order to answer the questions. Number 56 would take a bit of time to figure out. Check the box for each of the following that are paramagnetic. Right. For these and phosphorus, because phosphorus is going to be like nitrogen. You can look at this one. That's paramagnetic. Right? Let's see. How about an O2? If we look at O2 energy diagram. There we go, O2. Where are those unpaired electrons? They're pi 2p, pi stars. 2p. So we've got two electrons here. That means you've got one here, one here. Right? If we add an electron, this is the highest energy orbital. So if we add one, it's going to pair that one. But it's still paramagnetic. Now, it won't be, when you measure that diagram I showed you, where you drop the sample into the magnetic field and measure the force, it's going to be a lesser force because you've only got one paired electron. But it will still be paramagnetic. How about if we add two electrons? All right, now it's diamagnetic. We've got all paired electrons. So we've got this one. How about boron? Well, this one, just look at boron and say, boron has two unpaired electrons. Just look at the diagram. Two unpaired in the pi 2p orbital. Right? That means that they have to be unpaired because there are two places, two degenerate orbitals in the pi 2p. So this one's paramagnetic. Let that one go. Look at carbon. Carbon's all paired. Right? So that's not one. Nitrogen, I think they're all paired also. Yep. Those are diamagnetic. F2, they're all paired, diamagnetic. Now we get to the oddball. the Cn minus. So what we have to do is decide, is this have mixing or no mixing? Well, carbon and nitrogen are both from a region where you have sp mixing. So that's an easy call. So you would have carbon and nitrogen in that same order. And the highest, let's just write them all. Let's see, sigma, sigma star, pi. Sigma, sigma star, pi. Let's see, this is 2s, yes, 2s, 2s, 2p, and sigma 2p, and the pi star 2p and sigma star 2. We may not need all of them. Okay, valence electrons. Carbon has 4, nitrogen has 5, that's 9, plus 1 is 10, because this is an ion. So we need 10. 2, 4, 8. That would be diamagnetic. So far, so good. Yeah. And then P2 is going to look like nitrogen. And nitrogen is diamagnetic also. So diamagnetic, dia. These are the only 3 that are paramagnetic. Okay. Let's just go to 57. And scroll time. Yep, get it all in there in one shot. If we're missing. If we're missing that part. Okay, bond order for each of the following. Okay. Well, hydrogen's easy because it's just sigma from the 1s. That's it. And it's got 2 electrons in it. The next would be sigma star from the 1s, in case we make an ion. So this first one has 2 here. The bond order would be 2 divided by 2 is 1. Okay. H2 plus. So we've lost an electron. That means we've decreased by 1/2. Okay. H2 minus. So we're going to add 1 over here. And that also decreases by 1/2 because we added it to an anti-bonding orbital. How about Cn minus? We did that one before, didn't we? For that previous question. Yeah. Cn minus. Okay. Let's do, that's a plus right there. I know it's kind of hard to see. It's a plus. This is a minus. So let's do the Cn and work from the Cn. Then we can work out from that. Okay. So we're going to have, for Cn, we're going to have sigma 2s, sigma star 2s. Then we're going to have pi 2p, sigma 2p, pi star 2p, and sigma star 2p. Because it's mixing, inverted. Okay, so we have 4 and 5 is 9. 2, 4, and 4. 9, right? Yeah. Okay, so the bond order for this one is 4 plus 1 is 5, and 2 is 7. 7 minus 2 divided by 2. So that's 2.5, right? Okay, so that would be E, 2.5. Okay, now if we add an electron for D, where is it going? Now we got room here. So that would take this one up to 8 minus 2. Wait a minute, I did that wrong. Did I do that right? 2, 4, 2, 6, 7 minus 2. 5 halves is 2.5. That's right. Now, if we're going to add an electron for D, it goes here. So that's 2, 6, 7, 8. Oh, 6 divided by 2 is 3. Okay. And then if we subtract 1, we're subtracting it from a bonding orbital, which would decrease it by a half. So that would be 2. What I got. Okay, it agrees with the answer sheet anyway. All right. 58. This is the following. This molecule is called glycine. It is the simplest amino acid. You know, amino acids are used to construct proteins. And they're called amino acids because this is the central carbon here. There's your amine, and there's your acid, amino acid. So all you have to do to, you always have this fixed hydrogen here. This one can change. That's the one that changes the identity of the amino acid. If you, for instance, if you change this one, that's glycine. If you change this one to a methyl group found there instead, you would have alanine. You can do that for all the rest of them. 20, painting myself into a corner. It's either 21 or 23 amino acids in our proteins. That's not all the amino acids, but those is the ones that we use to make proteins. Okay, so let's get back to the topic. Indicate the hybridization at each nitrogen and carbon atom. All right, let's see. Let's draw it out over here. Carbon, carbon. Okay, that is. That's got to have a lone pair there to make an octet. I mean, you can draw the Lewis dot structure and verify it. And then this one has a carbon double bond oxygen, another oxygen over here, and a hydrogen. So this oxygen is going to have a lone pair and a lone pair here like that. Kind of like water. The water's the same way. It's 2 lone pairs. Okay. Duet, octet, 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 octet. Okay. So now we got all of our, that's the key to this one is defining, is put in the lone pairs because that will determine the hybridization. So the hybridization around C1, this is 1, this is 2, and the nitrogen. C1 is 1, 2, 3. sp2 hybridization. All right, over here. sp2 hybridization. This one is going to be sp3. It's got 4 groups. Nitrogen is 1, 2, 3, 4. sp3. Okay. What's the total number of bonds in the molecule? The total number of bonds, sigma and pi. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 bonds. How many pi bonds? Well, just look for the doubles or the triples. We've only got 1 double bond. So there's only 1 pi bond. Okay? You're ready. Let's see. Yeah, I might as well do this one. I don't think I need all that extra lines down here. Explain the concept of delocalization of electrons in SO3. Indicate how this idea relates to resonance. Well, SO3 is going to be, let's see, 4 times 24 electrons, right? Because sulfur and oxygen from the same group. So if we do the S, let's see, we have 3 oxygens. Okay, so that's 2, 4, 6 equals 18. That's 9 more. 3 times 3 is, not, oh, excuse me, that's 18 more. 2, 4, 6 times 3 is 18. Okay, so we're done there. All right, so if we make an octet, we can, from any of these oxygens, we can make a double bond there between oxygen and sulfur. But we can also make one here. Or we can make one, and I'm not drawing, that should be trigonal planar. Here, here, and here. So, all right, so we have to resonate these structures. We're resonating between among three equivalent Lewis dot structures. And we do that because we need an octet on sulfur, and the only way to get it is to take one of the lone pairs from oxygen and make a double bond. But since all of these oxygens are equivalent, we can make 3 different double bonds. Let's see. Delocalization. The concept of delocalization. Now, this is the way it would be for the valence bond theory or the localized electron model. We would have to write it this way. But when we consider delocalization, what we're saying is that this pi structure, this is where we bring in molecular orbital concept. Right. Delocalization says that these pi electrons belong to the whole molecule. So if we did that, we would draw structures something like this. Or we could say, if we were looking at the electron distribution, we would draw it something like this. And the delocalization of that pi bond is over the whole molecule. Okay, something like that. Now you can look in the key. I'm sure the key is in Blackboard and check my wording. But that's the gist of the problem. If we go from resonance to delocalization, this is what you get. Those delocalized pi electrons belong to the whole molecule, not just to each individual. It's kind of a, we're walking along the fence. On one side is the localized electron model, and the other side is the molecular orbital model. Okay, 60. Let's see here. How much of this I can get on the board? Oh, the whole thing. There we go. All right. Consider these 3 molecules. Molecule A, B, and C. Molecule A has a hybridization of sp3. That's given right here. Molecule B has 2 more effective pairs of electrons around the central atom than molecule A. Molecule C consists of a sigma bond and 2 pi bonds. Give the molecular structure, hybridization, bond angles, an example. Okay. Let's work with this one first. The molecular structure. Now that's assuming hybridization of sp3. The molecular structure here, we have to assume that we're dealing with no lone pairs. To have a molecular structure with sp3, then we would have to have trigonal planar. Okay. And the bond angles would be 120 degrees. So what's an example? This is a good one. Boron trihydride. But wait a minute. Oh, scratch that. I'm going to read my own sp3 hybridization. You should copy this. sp3 is tetrahedral. Bond angles 109.5. And methane. There you go. Molecule B has two more effective pairs, electron pairs, around the central atom than molecule A. It has two more pairs. If we've already got 4 pairs to give us sp3, then 2 more has to be D2sp3. 2 pairs need 2 more orbitals. So this would be octahedral. And the bond angles, if we draw it out like this, bond angles would be, and we're assuming here that there are no lone pairs. We have to assume that, otherwise we can't answer, right, for molecular structure. The bond angles would be 180, right, that. Or that, or this, or this, right? They're all 90 degrees. And what's an example of that? Well, let's see. 1, 2, 3, 4, 5, 6. Sulfur hexafluoride would be a good one. You won't have any lone pairs sticking out there. That's what our objective is. No lone pairs in order to meet this condition. Molecule C consists of 1 sigma bond and 2 pi bonds. 1 sigma. All right, so we have to assume 1 sigma. Let's see, if we did it this way, right, if it was diatomic, 1 sigma and 2 pi's would be like that. If we did it like this, that would be 2 sigmas. So we can't do it that way. If there's only 1 sigma, it has to be this way. Right? We're only that way. It has to be a triple bond. There's no other option. And the molecule would be linear. Okay. And the hybridization here, actually, the only way you can get it like that is to do this. And the hybridization on either one of those would have to be sp. And the bond angle would be 180 degrees. What's a good example? Well, how about N2? Or here's a better one. Carbon monoxide. That's what makes carbon monoxide nasty. Okay, let's see. Is that it? Oh, we got the last one. Draw a molecular orbital diagram for O2 and N2 using molecular orbital theory. All right, I made this one kind of easy because all you have to do is go back here to useful information and there they are. That part is easy. Draw the molecular diagrams for O2 and N2. And then using the molecular orbital theory, explain why O2, removal of one electron from O2 strengthens the bond, while the removal of one from N2 weakens the bond. Right, so after you draw the diagrams, then all you have to say is the bond order for N2 is 3, bond order for O2 is 2. And if you remove an electron from O2, you're removing an anti-bonding electron, which strengthens the bond. But from N2, you're removing a bonding electron, which weakens the bond. And that answers the question. That's it. We're done. Unless you have questions or comments.